Hello students. Successful and unsuccessful people in this universe do not vary greatly in their abilities. What is far more important is how one utilizes the abilities that one has. So with this positive note, we are going to study today. This is the first chapter of mathematics for class 9th. The name is real numbers. In this, there is a small topic called irrational numbers. So we are going to study today what are irrational numbers. Irrational numbers. We will be telling regarding this in two different ways. One is a number. While defining rational numbers, we said a rational number is a number which can be written in the form of P upon Q, where P and Q are both integers and Q is not equal to 0. Q being denominator there. Here we will just say it like this. A number, irrational number, is a number which cannot be written in the form of P upon Q. It cannot be written in the form of P upon Q, where P and Q are both integers and Q is not equal to 0. That is one way of defining irrational number. Another way of defining irrational number is a number is said to be irrational if its decimal expansion is non-terminating, non-repeating. So this point we will elaborate a bit. If I take say 1 by 2, the decimal expansion will be 0.5. If I take 1 by 4, it will be 0.25. If I take another number 1 by 8, decimal expansion will be 0.125. If I take yet another number 1 by 3, its decimal expansion will be 0.3333 and it will keep on going like that. If I take 1 by 7, its decimal expansion will be 0.142857. Again it will be 142857. See, I don't know whether that is visible or not, but this particular block 142857, 142857, this block will keep on repeating endlessly. So we have numbers whose decimal expansion terminates. Here if you divide 1 by 2, remainder will become 0 in the very first step and you will have the decimal expansion is terminating. If you divide 1 by 4, remainder will again become 0 and the decimal expansion will come 0.25. 1 is divided by 8, after some time remainder will again become 0 and you will have 0.125 as its decimal expansion. But if you divide 1 by 3, remainder will never become 0. But the digit you will find that it repeats. If you divide 1 by 7, remainder will again never become 0. But 142857, this is a block of 6 digits. 142857, 142857, 142857. 1 when divided by 7, you will get its decimal expansion like this, that it will never terminate but it will repeat. And here blocking, the repeating block contains 6 digits. Here it was only single digit. So such is the decimal expansion of rational numbers. If you find a number decimal expansion of which is terminating or non-terminating but repeating, these numbers are said to be rational numbers. So you can say a rational number will have its decimal expansion as terminating or non-terminating but repeating. Or if the decimal expansion of a number is non-terminating but repeating, or if it is terminating, the number is rational number. Now what about irrational numbers? Irrational numbers, we have already defined the decimal expansion of such numbers. Let me write here, say decimal expansion 0.10, 100, 100, 1000, and it keeps on going like that. So see, here decimal expansion is neither terminating nor repeating. First it is 10, then becomes 2 zeros, then becomes 3 zeros, and yet another one, right? If then it one becomes 4 zeros, 1 and 4 zeros, like this it keeps going. So if the decimal expansion of a number is non-terminating, non-repeating, it is neither terminating nor repeating, then we say it is irrational number. So irrational number is the one whose decimal expansion is non-terminating, non-repeating. Or if the decimal expansion of a number is non-terminating, non-repeating, that such a number is called irrational number. Now we will be talking about what real numbers are. See, the totality of rationals and irrationals forms collection of all the real numbers, which means only this, that if you want to have all the real numbers together, put every rational number and irrational number together. In simple words, you can say all the rational numbers and irrational numbers together form all the real numbers. So that was all about real numbers. And now representation of these numbers, real numbers on number line, if you say. So every point on a number line definitely represents a real number. Every point on number line definitely represents a unique real number, I can say. And every real number can be represented by a unique point on the number line. It is both the ways correct. Once again, let me tell you, every real number can be represented on a number line by a unique point. And every point on the number line definitely represents a unique real number. Now we will see how the real numbers can be represented on number line. So say if I want to represent under root 2 on number line, what I will do is I will take, say this is O, this is, let me say A, and let us say it is 1 unit length. At A, make a 90 degree angle, and 1 unit you have taken here, take again 1 unit length there. 1 unit, 1 unit. That could be centimeter or whatever it is. Now join these together. If this is 1 and this is 1, by applying, and let us say this is OB. So you see this is OB, 1 and 1. If you want to find out OB by applying Pythagoras, it will be OB will be square of 1 and under root of that. So this becomes under root 2. Now this length of OB is under root 2. But this is not on the number line. So for representing this on number line, take the compass, take O as center and OB as radius. And then you come on to this, put an arc, and the point of intersection of the number line and the arc will represent under root 2. Once again I am reading out the procedure for representing under root 2 on number line. Take unit length, let us say it is OA. At A, make 90 degree angle so that Pythagoras can be applied. Then take length AB, again 1 unit. And now if you want to find out OB by applying Pythagoras, the OB length becomes under root 2. Now if under root 2 be represented on number line with the help of compass, take O as center and OB as radius, and then put an arc. And the intersection, the point of intersection, let us say it is this, of the arc with the number line produced. That point of intersection will represent under root 2. This is true in case of under root 5 even. Say if I want to represent under root 5 on number line. So what I will do, there is yet another method, we will subsequently study that also. But this is spiral method, and we can make a spiral like thing. This is O, this is say A, this is unit length. Again 90 degree, 1 unit. Let us say this is B. Now this is under root 2. Make another 90 degree angle with this. And let us say this is C. Take unit length. That is under root 2, this is 1, so this will come to be under root 3 by Pythagoras. Similarly, you can go up to under root 5. Yet take another 90 degree angle with this 1, and this will become under root 4. So like this you say. Suppose now you want to write under root 5 or under root 3. Under root 5, for under root 5 we will have to take one more step. For under root 3 what you do? Take O as center and OC as radius, put an arc, and the point of intersection of your arc with the number line extended or produced will represent under root 3. Similarly, we can represent under root 5 also. So that was, so we have studied today what irrational numbers are, what are real numbers, what are the nature of decimal exponents of rational numbers and irrational numbers, and how real numbers are represented on number line.